Hi. So today we're going to be looking at thermal physics, right? So in thermal physics, this is chapter 3. So the reference book for this you can look at is the K.A. Sarkos physics book, okay? So this is the 6th edition, all right? Okay, so in this case, we start off by looking at thermal physics. So whenever we look at thermal physics, the first thing that comes to mind is the idea of thermal, right? So we're going to be looking at the idea of heat, energy, temperature, and those things. So the transfer of heat, the law of conservation of energy, and things like that. Okay? So whenever we start off by looking at thermal physics, we start off by seeing the idea of solid, liquid, and gas. So let's say if I have a solid structure shown over here, right? So you would have seen this diagram before, that whenever we have a solid structure, all of the atoms are bounded together like this, okay? So the atoms are still moving. So in this case, the atoms are still moving, so they are vibrating, right? So think of this as a solid piece of metal, okay? And let's say that if if this is aluminum metal, for example, then you've got your aluminum atoms that are inside. Okay? Now, basically the atoms are vibrating, but as you can see that they're not moving as much, okay? So therefore we can say that their kinetic energy is very low, and this means that their velocity is going to be low, okay? Now solids are characterized by strong intermolecular forces of attraction, okay? So they've got strong intermolecular forces of attraction, and that's why the particles don't want to move away from each other. So that's the idea of solids, okay? Now, in this chapter, what we'll be looking at is that we will be seeing that if you apply energy to this system in the form of heat, then the intermolecular forces of attraction will slowly start to break. Okay, so we'll be understanding how that happens. Now, the next thing that we can see is the next state of matter is liquid. Okay, now if you look at liquid states of matter, then when you have a liquid, the particles are still moving. So the particles are moving, but they're further apart from each other. Okay, so in this case, as we can see over here, that the intermolecular force of attraction is a bit weaker, right? So in this case, intermolecular forces of attraction are weaker than solids, okay? So they're going to be weaker than solids. So what we see over here is that the kinetic energy rises and the velocity is also rising, so the particles are moving around more, okay? Now after this we come to gas. So in gases you have virtually no intermolecular forces of attraction, okay? So gases are, if you have a gas over here, there's virtually no force. So in this case, virtually no intermolecular force of attraction, okay? So because there is no intermolecular force of attraction, the kinetic energy becomes very, very high, and the velocity is very high because the particles are free to move, right? So there's no force that is forcing them to stay close together, okay? So in this case, that's the idea of solids, liquids, and gases, right? Now, after this, what we can see is we can look at the total mechanical energy in this system. So as we looked at it in forces, the total mechanical energy of any system, right? The total mechanical energy of any system is just the sum of the kinetic energy plus the potential energy, okay? So the kinetic energy is very simple. We know that this is 1/2 mv squared, but every state of matter, you're also going to have some form of potential energy. And so this potential energy comes from the bonds. So they're like chemical bonds, okay? So you can have ionic or covalent bonds, and that's where the potential energy comes from. And one way to think about it is, if you're looking at metallic structures, then metallic structures, you've got these basically, if you look at the metallic structures, you've got these positively charged ions in a sea of electrons, right? So in this case, atoms in a metallic solid, right? If you have got atoms in a metallic solid, then what's going to happen is that they're going to be close to each other, right? So this is what you're going to get. But at the same time, these in this electron sea model, the atoms would end up losing their outer electrons, and so these would become positively charged ions because they're losing their electrons, okay? So because they're losing their electrons, then the atoms become positively charged, and then you get these electrons that are freely moving in the solid, okay? So these, in terms of key terms, these are a sea of delocalized electrons that are free to move randomly throughout the fixed lattice of positive ions, okay? So this is a sea of delocalized electrons, and it can move freely through the lattice of positive ions. And the main point over here is that the electrons have a negative charge and the ions has a positive charge. So you will learn this later on, where basically the forces between two charges is given by k, q1, q2 by r squared, where k is a constant, and then q1 and q2 are just the charges, the magnitude of the charges, and r is the distance between them. So, in a metallic structure, you can think of the potential energy that is coming from this electrostatic force of attraction. Okay? So I think that's enough chemistry. The main idea, just to note, is that solids, liquids, and gases, the mechanical energy comes from the kinetic energy and potential energy. Solids have very low kinetic energy, right? Liquids also have relatively high kinetic energy, but not too high, and gases have very, very high kinetic energy. Okay? Now, after this, the other main idea when we look at thermal physics is this distinction between temperature and heat. Okay? So this is going to be this distinction between temperature and heat. So we start off by looking at temperature. So in this case, temperature, which is over here, temperature is proportional. So the temperature of an object is proportional to the average. So it's proportional to the average kinetic energy. So it's proportional to the average kinetic energy of the particles in a solid, liquid, and gas, or in a substance. Okay? So essentially, you would have different, let's say if you have different particles in this metallic structure, then each of them will have a certain velocity v, so we can call it vi. But if we want, we would take the average velocity. So we would sum up all their kinetic energies. So we would just take the sum of kinetic energies. So this is a summation symbol. So you'll just be summing up 1/2 mvi squared. Okay? So this vi is for the individual velocity of every particle, which will differ. And you will just summate this. So you will go from I is equal to 0. So let's say that this is the 0th particle, then this is the first, second, third particle, fourth particle, and so on. So you'll go from the 0th particle to the nth particle. So let's say if there are n particles in a substance, So you will go from 0 to n, and then to take the average, you divide the whole thing by n. Okay, so this gives you your average kinetic energy. So the way it happens is, let's say if I have a group of numbers 2, 4, 6, and 11, then if you want to find their average, you first sum them up, and then you divide it by the number of numbers over here, which is 4. Okay, so this average comes out to be 23 by 4, which is 5.75, I think. Okay? But yeah, so the main idea is that you want to look at the average kinetic energy. So when you take the average kinetic energy, you sum it up, divide it by the number of particles, and this is what you get. Okay? Okay, so whenever you think of temperature, you should remember that this is proportional to the average kinetic energy. Okay, that's what the temperature is proportional to, right? Now after this, we can look at some scales for temperature. So till now, you would be very familiar with the Celsius scale, right? So the Celsius scale is a scale to measure the temperature, and this scale is basically depending on the. So this scale ends up depending on the melting and boiling point of water. Okay. So what we see in this scale over here is that what they said is that the melting point of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. And so they took every temperature relative to the scale. Okay? So that becomes your Celsius scale, where every temperature is relative to the melting point of water, which is H2O, and the boiling point of water. Okay? Now, there is another scale which you may have seen before, and this is called as the Kelvin scale. Okay? So the Kelvin scale is just based on the idea of absolute zero. So the absolute zero comes from the fact that there is a certain temperature when the kinetic energy in a substance. So there comes a temperature where the average kinetic energy in a substance is basically just 0 joules. Okay? So an object can be so cold that the particles in the substance are not moving at all, which is why their average velocity is 0, so their kinetic energy would be 0. Okay? So what they ended up finding was that when you have negative 273 degrees Celsius, that's when you get 0 Kelvin. Okay? So 0 Kelvin is the absolute zero, and in Celsius terms, it has come out to be negative 273 degrees Celsius. Okay? So if an object is at negative 273 degrees Celsius, they basically say that, the kinetic energy of the particles is virtually 0, and that none of them are moving. So there's no movement. Okay? Now, so if you have to convert between the Celsius scale and the Kelvin scale, then this is a linear conversion. So that makes it very convenient. Okay? And what I would recommend is just take one value which you remember and then just convert it linearly. So for example, I remember that 25 degrees Celsius is 298 Kelvin. And then let's say if they want you to calculate the temperature in Celsius at 300 Kelvin, then you can just do a linear conversion. So you can say that 25 plus 22 degrees Celsius is 298 plus 22 Kelvin. 298. So this would just be 25 plus 2 degrees Celsius is equal to 298 plus 2 Kelvin, right? And so you can see that 27 degrees Celsius is 300 Kelvin. Okay? So just remember one of the temperature, and then based on that, you can convert it to Kelvin. Okay? So that's the main idea about this. Alright? So now what we can look at is we can just do a simple example, right? So let's say if we do a simple example over here. So let's say that if the temperature of an object rises from 10 Kelvin to 30 Kelvin. Okay, so now let's say, so they're saying that can you show this temperature change in Celsius? So can you show this temperature change in Celsius, right? So the main thing you need to understand is that the conversion between Kelvin and Celsius is linear. So in this case, the change in Kelvin is 30 minus 10, which is 20 Kelvin. And so the change in temperature in Celsius degrees will just be 20 degrees Celsius. Okay? So yeah, we've looked at temperature, we've looked at degree Celsius, degree Kelvin, right? Main thing for temperature is you need to know that the temperature is proportional to average kinetic energy. So you sum the kinetic energy of every particle by using the summation sign, and then you divide it by the number of particles to get the average. Okay? Okay. Now, after this, we can look at the idea of measuring temperature. So this one is a fairly quick idea, right? Now, when we look at measuring temperature, the main idea is that so if you have an ice cube, for example, let's say if this is an ice cube, so you would have noticed that, if you melt this ice cube, it turns into water, and you would see that the volume of water is higher, right? And then in this case, if you make this small piece of water, if you make it into water vapor, suddenly the volume of this water vapor is even higher, right? So solids have a low volume relatively. Liquids have a little bit higher, but gases have massive volumes, right? I mean, sort of just think about the atmosphere, right? The air that you breathe, it fills up the entire room, right? Whereas, let's say the cup of coffee that is in front of your table, for example, it's just a cup, and the volume it fills is relatively less, right? So what this basically means is that there is a property that if the temperature of an object rises, so if the temperature of an object rises, it would expand. Okay. Now there are exceptions to this. Sometimes you have something. Yes, there are exceptions to this, but conventionally speaking, when the temperature of an object rises, it should expand. Okay, and that's what some of these thermometers would be using. So you would have seen this mercury thermometer, liquid mercury thermometer. So in this liquid mercury thermometer, what would happen is that you have this vial within this thermometer, and over here you've got some temperatures. So let's say for the human thermometer, 36 degrees Celsius, 37 degrees Celsius, 40 degrees Celsius, and then let's say this is 30 degrees Celsius. Okay. So what you would see is that you would have some mercury in this vial, and whenever you measured your temperature, then let's say if you had a very high temperature, then this mercury would expand. Okay, and the mercury is a liquid metal, so it has good conductive properties, right? So now in this case, what happens is that the mercury is going to expand, and once it expands, the higher it expands, the higher your temperature would be. So let's say if someone has a very high fever, the mercury will expand all the way over here, right? So that means they have a very high temperature. If a person has normal temperature, the mercury won't expand as much. Let's say 35, 36 degrees Celsius or so. Okay? So that's the main idea for any sort of thermometer, that if you have an increase in temperature, then the mercury expands, and based on that you can measure your temperature based on the expansion. Okay. And for those digital thermometers, they look at thermal resistors. So you would not really need to know that, right? So yeah, you have you don't really need to know those things. I don't think they'll test you on it. But yeah, basically for those digital thermometers, they would have, so you know, in a digital thermometer, let's say if you have a circuit where you have a battery, and then let's say you have some resistance value, right? Okay, so it's sort of like one of these values, like the resistance, will change. So the resistance will change due to the temperature, right? So they would have some variable value where some quantity is changing relative to the temperature, and then based on that they'll calculate they'll give you your temperature. Okay. Okay, so now we can go to the important thing, right? So this is the important thing over here. The important thing is the difference between heat and energy. Sorry, the difference between heat and temperature. Okay? This is a very important distinction to make. Now, in this case, you can think of temperature, as we have seen. So temperature is just the average kinetic energy of all particles in a substance. So it's average kinetic energy of all particles in a substance. So that's what temperature is proportional to, right? So temperature is proportional to average kinetic energy of all particles in a substance. Okay? But in this case, heat is not the average kinetic energy. Heat is the total energy in a substance. Okay? So basically, what this means is that the official way to define heat is that heat is the energy that is transferred. So heat is the energy that is transferred from one body. So it's transferred from one body to another due to a change in temperature difference. So due to change in temperature difference. Okay? So what this states is that heat is the energy you're transferring from one body to another due to a temperature difference. So, you know, let's say if I have a very, very cold object, and then let's say I bring it in contact with a very, very hot object, then you're going to get a heat transfer from the hot object to the cold object. Okay? So this is an energy transfer, and this specific energy transfer, we are going to call it as heat. Okay? And the reason, so in this case, the main thing is that this heat transfer will keep on occurring, right, until, so this is important, until the temperature of both objects is same. Okay? So what this means is if you bring in two bodies in contact, and let's say they have different temperatures, one is warmer, one is colder, then you're going to get an energy transfer, and this specific energy transfer is called as heat, and the energy transfer will keep on happening until the temperature of both objects is the same. So let's say that if this is 100 degrees Celsius and this is 10 degrees Celsius, then you'll get a heat transfer, and it will keep happening until both objects have the same temperature. Okay? Now, you would be thinking that if you want both objects to be the same temperature, so let's take this example. Let's say the cold object is 0 degrees Celsius. So you would be thinking that the heat of the bigger object will go to 50 degrees Celsius, and then the heat of the smaller object will go to 50 degrees Celsius, and then the temperature change will stop, right? Or the heat exchange stops. But the thing is that in this case, it's not so simple. And you have different factors which we will be learning later. You have to consider the mass of the substances. You would also have to consider the nature of the substances. Some substances can lose heat very easily, some can't. So you have this specific heat capacity which we will be learning. Okay, so don't make the misconception that you just take the average of both the temperatures. So you do like 0 plus 100 by 2 and you're done, right? So it depends on the factors which we will be learning later. And a lot of the numericals in this chapter are just going to be about heat transfer, right? So we're going to be measuring the initial and the final temperatures of different objects when they come into contact with each other. Okay? So once again, just as a summary, heat is the energy that is transferred from one body to another due to a change in temperature difference. And in this case, the heat transfer will keep on happening until the temperature of both objects stays the same. Okay? So that's the main idea for heat. And then, so that's the heat, right? And then you see that this heat is proportional to total energy in an object. So heat is proportional to total energy, and in this case, temperature is proportional to average. So this is important. Heat is total, temperature is average kinetic energy. Okay? So in this case, we can define another term which is known as internal energy. Okay? So internal energy is basically so the internal energy is sort of just the total energy, or this is the total mechanical energy in a system. So this is the total mechanical energy, or we can just call it as total energy. So heat is the total energy of particles in a substance. Okay? It's the total energy of particles in a substance. So you're going to get the kinetic energy, and you're also going to get your potential energy, right? So if you add up the total kinetic energy and the total potential energy of all the particles, then you'll get the total internal energy of a substance. Okay? So that's the idea. So now that you have seen, the temperature is related to average, heat is related to total. Okay? So let's look at this example over here. So let's say that if you have a bathtub, right? So this is a bathtub, and let's say that this is a bathtub of boiling water. Okay? It's got a boiling water, it's fully filled. So think of a bathtub, and let's say that the water is at 100 degrees Celsius. Okay? And now let's say that you have a matchstick. Okay? So this is a matchstick over here, right? And let's say if you're given two options, okay? Let's say you have to be in this bathtub for, let's say, 30 seconds, right? So you have to fully be in this bathtub for 30 seconds with 100 degrees Celsius of boiling water, or you would have to touch this matchstick for 30 seconds, right? And just remember that the temperature of the matchstick, we can put it as, let's say, 160 degrees Celsius. Or actually, let's make it a bit higher. Let's say 200 degrees Celsius. Okay? So which option would you choose, right? So yeah, most of the people would say that they would rather be in the water, because they would think to themselves that, oh, it's only 100 degrees Celsius, and the matchstick has a higher temperature, and so the matchstick would be more dangerous. But the main point is that this is a matchstick, so even though it has a higher average kinetic energy, so temperature is proportional to average kinetic energy, right? So even though the matchstick has a higher average kinetic energy, in this case, the overall heat and the overall energy in the system is relatively low. Okay? Whereas even though the water has a lower temperature, right, the temperature is lower, but the heat is very, very high. because the total energy is very high, right? So that's the difference between heat and temperature. Okay, so normally we would say that, oh, if the temperature is high, it's very hot in conventional terms, but in terms of physics, this is the difference between them. Okay. Okay, now, like we said, heat is the energy transfer. So heat is the energy transfer when two objects of different. So heat is the energy transfer when two objects of different temperatures come into contact, right? So that's what heat is, and then the internal energy is the total energy of a system. So what this means is that the internal energy, so in this case, the internal energy of a system, can be changed, right? The internal energy of a system can be changed if heat is added. So if heat is added or taken out from the system, Okay? Now, like we were saying over here before, like how we were saying, when you had two objects, and let's say that if this was at 100 degrees Celsius, and then let's say that this was at a 50 degrees Celsius or 0 degrees Celsius, then you're going to get a temperature, you're going to get a heat exchange going on. And there might be a misconception that the heat exchange will stop when the temperature of both objects is 50 degrees Celsius, but that's not the case, right? Because the final temperature depends on a lot of different factors. So if you think about it, if this is your final temperature, first of all, the final temperature will be proportional to the overall energy, right? So for example, if this is 100 degrees Celsius, and let's say if I change this to 1000 degrees Celsius or 10,000 degrees Celsius, then obviously the temperature of both objects will be higher if the overall energy in both objects is higher, okay? So the temperature is proportional to the overall heat, and we can also say that the temperature is inversely proportional to the mass. So for example, let's say if we have 10,000 kilograms of mass, and let's say that this is 5,000 kilograms of mass, right? Or, sorry, actually the way you can think about it is that in this case, the way this happens is that, let's say if I have 10,000 kilograms of mass, right? And I apply 1,000 joules of heat, then we will see that the temperature change will not be that high. It will be non-existent, right? Because the mass is so high that you need a lot more energy to cause the temperature to rise, okay? But then in this case, let's say that if I have 0.0001 kilogram of this mass and I apply 1,000 joules of energy, then you will see that the temperature will rise massively, right? Because when you have a lower mass, you have lower number of particles, right? So lower mass means lower particles, which means that you need less particles to provide the energy to. So 1,000 joules of energy will actually be going to much lower particles, right? And so the particles will start to move on faster and faster. And when the particles move faster, then the temperature rises because the kinetic energy will rise. Okay? So that therefore you can say that the temperature is proportional to 1 divided by the mass. Okay? So it's like if you increase the mass, then the temperature change will go down. But then if you decrease the mass, then the temperature change will go up. Okay? So you can think of the relationship like that. And then the last one is that in this case, you can see that this temperature exchange will depend on, so the temperature exchange will depend on the specific material we are looking at. Okay? So some materials in this case can increase the temperatures very easily, and others cannot because they're not, because other materials would be insulators, right? So you can think of it this in terms of let's say if you have let's say if it's cold outside, right, and you go and sit on a metallic chair, then immediately what you're going to feel is that the chair is going to be very cold, right? But if you go outside and let's say you sit on a wooden chair, then you will see that it is still relatively warm, right? So if you touch a metallic pole in winters, let's say, especially in Canada, when you look at any sort of place like that, then you will find that these are very, very cold. Okay. So the temperature change depends on the specific substance that we are looking at, right? So we have a term for this which is called as C. So C is the specific heat capacity. Okay, so the specific heat capacity, the formula for it is joules per kilogram per Kelvin. And so basically specific heat capacity is the energy required. So this is the energy required to increase the temperature. So it's the energy required to increase the temperature of a unit mass. So unit mass is 1 kilogram of a unit mass of a body by 1 Kelvin. Okay. So some substance, if you give them little energy, the temperature rises a lot because they're very good conductors. Other substances, you give a lot of energy and their temperature would not rise as much, right? So this is the energy required to increase the temperature of a unit mass of a body by 1 Kelvin. So that's specific heat capacity. Okay. So the main thing is, when you take all of these proportionalities and when you take all of these proportionalities together, and when you mix when you take all the variables together, you get that the overall energy or the total heat is mc delta T. So delta T is the change in temperature. This is Tf minus Ti. So this is final temperature minus your initial temperature. C is your specific heat capacity, which we have learned. And M is the mass. And then Q is the heat, and you can think of it in the terms of energy. So the energy is in joules. Okay, so energy, which is in joules, is equal to the mass, which is in kilograms, multiplied by the specific heat capacity, which is given by joules per kilogram per Kelvin, multiplied by the temperature change, which is given in Kelvin, right? And as you can see, if you do the cancellations, then you get the same thing on both sides. So this is mass, specific heat capacity, temperature, and this is energy, Q. Okay? So that's what we get for Q is mc delta T. Now, after this, the important thing we can also look at is the law of conservation of energy. Okay? So this is the basic idea on which the numericals are done. So you would need to know this. Okay? Now what this states is that according to the law of conservation of energy, the energy can neither be created. So the energy can neither be created, right, nor be destroyed. So energy can neither be created nor be destroyed, but only be transformed. So energy can neither be created nor be destroyed, but only be transformed from one form to another. Okay? So the main idea is if you have got two substances over here, and let's say that if you have an energy exchange, so let's say that this is 100 degrees Celsius and this is 0 degrees Celsius, and these are two substances, then we can clearly see that the temperature of the first substance will drop. So the first substance will lose energy So energy is lost, right? And then for the second substance, the temperature will rise, so we will know that the energy will gain, so the substance will gain energy. So this will go up, right? Now, if you look at this entire system as one thing, so we isolate it from the rest of the world, we just look at this system alone and nothing else. What we can see is that for this one system, the net change in energy must be zero according to the law of conservation of energy. So the net change of energy is zero. So therefore, the energy is neither being created nor it's being destroyed. You're only transforming it, let's say, from object A to object B. And so because of that, because of this, the main idea that comes in is that in this case, if the first object A has lost energy, and then let's say, so this is A, so A loses energy, and let's say that object B has gained energy, then the sum of this must be zero. So this is a very important thing, okay? And yeah, before continuing, I'll just say that, this for copyright and stuff. So this belongs to Deep Think Math, this video, Deep Think Mathematics, all right? And yeah, so we'll be providing videos to help you with your examinations, okay? So yeah, it belongs to Deep Think Mathematics. All right, that's good. So now that we've got that out of the way, we can simply say that the energy that is lost plus the energy that is gained is zero. Okay? So these are the main things when we are going to be looking at heat exchange. So the main things we get over here is that, first of all, Q is equal to mc delta T. This is important. Second of all, energy lost in a system. So energy lost by an object plus the energy gained by another object is equal to zero. And the third thing is that heat transfer only takes place until temperature of both objects is same. So until temperature of both objects is same, right? And then the other thing you just need to know is that the temperature is proportional to your average kinetic energy. And in this case, heat is proportional to the total energy. And this total energy comes from two components, which is your kinetic energy, and then this is your potential energy. Okay? Now, in the coming videos, we're going to be looking at some worked examples. And then after this, we'll be looking at the phase changes, so latent heat and things like that. Okay? And yeah, so bye for now.